Recall that a vector is basically a value which has both a magnitude or length and a direction, and it can be represented graphically by a directed line segment. Now we say that two vectors are equivalent if they share both the same magnitude and same direction. So for example, these two vectors, which have the same length and same direction, are equivalent. And since I can place equivalent vectors anywhere in my coordinate system, and as long as they share the same length and direction, they are equal, I can have a lot of different ways of graphing it. So for simplicity, we say that we can graph a vector in standard position if its initial point is at the origin and it shares that same length. Now vectors can also be represented algebraically in two forms. The first is component form, and that's basically very much like a point, except it has arrowed brackets, and rather than the coordinates of the location, it's the change in the x values and the change in the y values, which are represented in those corresponding parts. For simplicity, I'm just going to call the change in the x values component A and the change in the y values component B. There is also a unit vector notation where we can say that a vector which has components A and B can be represented in unit vector notation as AI plus BJ. Now let's do an example so that we can see how this actually relates to vectors. So say I wanted to find a vector v, which sometimes has a vector notation hat over the top of it, that has an initial point or starting point 2, -4, and a terminal point or ending point 4, 7. Well, to represent it in component form, I first need to find what the change in the x values are. Well, from 2 to 4, I have increased 2 units. So the x component of its component form will be 2. And the y values from -4 to 7 have increased 11 units. So the y coordinate, or the y component, will be 11. In its equivalent unit vector notation, that will be 2i plus 11j. Now, since we said that a vector has both a magnitude and direction, there are two other things that are related to vectors that we can find given its component or unit vector notation form. The magnitude of the vector is basically just the size or the length that the vector is. It gets represented with a double absolute value symbol. So in an example where the magnitude of the vector -4, 3, which I will call vector W, if I wanted to find the magnitude of W, we represent that with the following notation, and it's calculated by simply squaring the change in x values and the change in y values and adding them together. You may recall that this is also the distance formula from geometry. For my specific case, the change in x values is just the x component of the vector, so this will be -4 squared plus the change in y values are the y component of the vector, 3 squared, which gives me the square root of 16 plus 9, which is just the square root of 25, or 5. So the magnitude of vector W is just 5. Recall that a unit vector is a vector which has magnitude 1. And if I wanted a unit vector in the direction of W, all I would need to do is divide vector W by its length. Since it has length 5, if I was to divide it by 5, it would then have length 1. So if I wanted a unit vector, which I'll call U, in the direction of W, I could merely divide W by its size or magnitude. And if I divide it by 5, everything having to do with vector W will now be 1/5 the size that it was, including its magnitude, which would make it magnitude 1. Thus making U a unit vector. So the unit vector, U in the direction of W, would be -4 divided by 5, comma 3 divided by 5. If I wanted a vector of any other length, I could then take this unit vector and multiply it by my desired length. Another value that we are sometimes concerned with when relation to vectors is the direction angle. So the magnitude was its size, the direction angle is its direction, which are the two things that define a vector. So I'm going to reuse the same example, vector W, which has components -4, 3, And I'm going to find the direction angle. So to find the direction angle and make sense of it, I'm first going to give it a quick sketch. I'm going to sketch W in standard position, which has initial point at the origin. It moves back 4 units in the x direction, negative 4 units in the x direction, and up 3 units in the y direction. So to find the direction angle, which is the angle measured from the positive x-axis to the vector, which I'll call theta, I'm going to first draw a reference triangle. I know that this side of the triangle has length -4, and this side has 3, and I'm going to find this angle to help me find theta, my reference angle, x. Well, in my reference triangle, I have the opposite and adjacent sides, so I can use the tangent ratio, and it would be related to 3 over -4. To determine what x is, I'm going to note my quadrant, and I'm in quadrant 2. That's where my terminal side of my vector is, so I'm in quadrant 2. And my reference angle, x, would be equal to the tan inverse of the magnitude of the ratio, which is 3/4. To determine what that value is, I'm going to use my calculator. So with my calculator, I'm going to type in tan inverse of 3/4, and I have my angle, 36.869 degrees, which I'm going to round to 36.9. Now to find my actual direction angle, since I'm in quadrant 2, and the end of quadrant 2 is 180 degrees, and my reference angle goes back 36.9 degrees, my direction angle would be 180 minus 36.9, which would be equal to, again, I'll use my calculator. I have 180 minus my previous result, which is 143.1. So that's my direction angle. So again, because a vector has both a magnitude and a direction, we should be able to, from its component form, describe both its magnitude, which is its length, and its direction, which can also be represented by a degree angle. Besides these two values, you should also be familiar with vector operations. Now, vector operations are very simple. Say I had a value, say I had two vectors v and u, and I wanted to represent 2 times the vector v. Well, anytime you're multiplying a vector by a scalar value, you simply distribute that 2 to each of its components. So 2 times 3 would be 6, and 2 times 5 would be 10. So this gives me the component form of the vector 2v, the vector which is twice as long as vector v. If I was doing a linear combination of v and u, say I had 2v minus the vector u, or minus 3 times the vector u, I would simply do that same multiplication. 2v from the previous step I already know is 6, 10. Then subtract 3u, well 3 times -1 would give me -3, and 3 times 8 would give me 24. Then when I combine these two vectors, I simply combine their corresponding components. So that would be 6 minus -3. Well, when I subtract a negative, it's the same as addition. So 6 plus 3 would give me 9. And then I'd have 10 minus 24, which would give me -14. So those are vector operations. Remember that any scalar multiple distributes the components, and when you're combining two vectors, you should combine their corresponding components.